remembers email before Gmail? Who remembers the massive amount of spam that we used to get before Gmail? Still do. Yes, we do. I remember when I switched from having my Excite email account to having Gmail, it was like entering a new haven where I didn't have to spend all of my day marking things as spam or not spam and deleting things out of my inbox. It was wonderful. Who remembers these? When I was a kid, I listened to my favorite radio station and I'd have a cassette in the tuner, waiting for that opportune moment where I could run across the room and hit record. About after 6 hours or so, I'd have maybe 20 minutes of a good mixtape. Of course, I no longer have to do that because I have Spotify, I have Pandora on my phone. It's really amazing because I don't have to spend any time making mixtapes anymore, although they are kind of fun to make. What do these two things have in common? They're both using data to solve a problem, to make our lives much easier. Pandora makes our life easier. Gmail makes our life easier. Spam filtering, really. So today, I'm here to issue every single one of you a challenge, and that is somewhere in this room, there is somebody who's going to make the next Gmail. They're going to make the next Pandora. Or maybe it's a group of people. Data, as we all know it, is a big deal. Data, big data, whatever you want to call it, it's a bunch of marketing humbo-jumbo, but it is a big deal. Data is the new bacon. I really like this shirt. I don't actually eat bacon, but this is so awesome. But you might be saying that I am at the wrong conference. I'm not at Java 1, I'm not at PyCon, I'm not at ClojureCon. This is not a big data conference, this is a Ruby conference, and I must be in the wrong place because Ruby is not a big data language. But I am going to agree with what Ben pretty much pointed out before this talk, which is that Ruby has lots of tools. Ruby has plenty of tools, whether it's in C libraries, regular Ruby gems, Java through JRuby. Ruby has many tools. But unfortunately, a lot of us don't know how to go about solving data-type problems because data science, machine learning is kind of a big freaking mess. If you were to open up a journal on machine learning, you would see lots and lots of comments about things that most of us don't understand because, honestly, most of the academics are trying to understand it themselves. On top of that, Ruby is not about complex math. Math's created Ruby for our happiness. Complex math was not created for our happiness. But that can actually be in our favor because Ruby is such a wonderful language. I personally love working with Ruby. Next slide, come on. And my computer is freezing. How wonderful is that? It must be the complex math. Now this next slide that is supposed to come up, which my computer really is freezing, how wonderful is that, is talking about who I am. My name is Matthew Kirk. I have been doing data science type things, machine learning for 8 years, a long time, before I even realized that it was even called machine learning. I learned it as operations research a long time ago, and I've been doing Ruby for 5 years. I really love both. I love Ruby and I love complex math. I like machine learning. Let's try this. Come on. There we go. On top of that, I'm actually writing a book about using machine learning with Ruby. And this talk that I'm going to be giving today is a chapter out of the book. Today, we're going to cover feed-forward neural networks. Doesn't that sound exciting? Come on, I want some more out of the audience. All right, neural networks is an extremely vast subject, so we're going to condense it quite a bit because this is 30 minutes long, and so we're only going to talk about feed-forward neural networks. There's plenty more that you can learn about, but let's just focus on one thing. We're going to go through an example of how to classify strings to a particular language, and we're going to do it in a test-driven fashion. And just to prove to you that I'm not making things up, we're going to actually demo it at the very end. So neural networks. Neural networks are a supervised learning method, which you remember from the last talk is basically the idea that you have data points that have particular labels, and you want to learn something off of that, a particular pattern. Neural networks are really interesting because you really don't have a lot of restriction. You can map just about anything with them. So that's why I like to call them kind of a sledgehammer. They're really good about taking any functional approximation and just making it happen. Now, if anybody has ever done computer science, most likely you've heard about neural networks a little bit, and some of you probably have seen a graph like this. Anybody? All right, so some of you. Neural networks are split up into 3 different layers. Now, you have the input layer, which is simply just the inputs. These are 0 to 1 binary type inputs, true-false type inputs. Really, it's pretty simple to know. It's just the input of what you're looking at. The thing that confuses people the most would have to be this hidden layer, whereby we're adding complexity to this particular function, and we can't see what's going on in there. It's more or less like a private method of this function. We don't see it, we can't observe it, it's just there and we know it's there. And lastly, we have the output, which again is just an output out of this function. Now inside of these neural networks, conceptually, we have neurons. And if any of you have ever taken biology, we all have neural networks in our brains, and we have little neurons that are talking with other neurons. It's the same idea with artificial neural networks, except that artificial neurons, which are these little pieces, are just a weighted sum. Now, x1, x2 weighted together and then wrapped in this function, that doesn't mean anything, right? It doesn't make any sense. So I think a better analogy is thinking about logic. Neural networks and perceptrons, any of those types of things, was based on this idea of threshold logic, where you could input data and you could determine whether it is true or false. Very similar to a digital logic gate, or Boolean logic where you're saying this and that. Very simple. But neural networks takes it a little bit further with fuzzy logic. No longer do things have to be 0 or 1. It can be kind of true or kind of false. It's a range between 0 and 1. Now, this is extremely powerful because no longer does things have to be black or white. You can really bask in the gray area. And so this is an extremely powerful piece of neural networks. But really, this analogy is probably the best idea to get us understanding what this particular neuron does. It takes 2 inputs, it adds them together in a particular logical way, just like this digital logic gate would, and then outputs the signal to the next neuron. Now, if we were to go back, you'll notice that we have this weighted sum wrapped in a function. Now, let's assume that we have x1 is, say, 20,000, and x2 is 50,000, and the w's are just both ones. It's going to make a very big number come out, and really that's not between 0 and 1. So all this function does, which is called an activation function, this, it takes any input and makes it between 0 and 1. Now, these are a lot of different funny mathematical terms that I don't expect anybody to take away from this because it doesn't really matter. Just realize that there's the learning curve, the bell curve, line, threshold. But the most important thing to take out of this is really the learning curve. Now, we all know that when we start learning something, we suck at it. So we start at the bottom, And then we get better. And then we plateau. That is the learning curve. That's all the sigmoid function and the Elliott function does. It takes a big number like 50,000 and makes it closer to 1, whereas negative 50,000 would be closer to 0. So all it's doing is making sure that it's true or false. Now there's one piece that I've left out of this, and I'm kind of hand-waving a lot of this because we only have 30 minutes to talk about neural networks, and that is finding the weights in these sums. Now, you could brute force that, and that would take an inordinate amount of time, or you could do it much more intelligently. People have come up with something called training algorithms, quick prop, rprop, backprop. Rprop is the fastest. But what you need to know is that really what we're doing is we're trying to minimize error. And the way all of these algorithms do it is simply something called gradient descent. So imagine that I was at the top of a hill in the middle of a fog, really, really thick fog, and there was a tree in front of me, and somehow I'm the aim guy. And I want to get to the base camp, right? Because that's all I care about at that particular moment. I can't see anything in front of me. All I can see is right what's in front of me, right? So intuitively, what I would do is I'd look around me and I'd see which direction is going down the steepest, and then walk that direction. And then again, keep doing that until eventually I hit the bottom of the valley. That's what all of these algorithms do, except the bottom of the valley is error. This error rate is pretty much, given a model, how often do we expect it to be wrong? We want to minimize this error so that our model effectively models the data that we have. That is just the tip of the iceberg. Neural networks is an extremely dense subject. You can get into RBF networks, deep learning, cyclical networks. There's tomes of volumes of written things about neural networks. It's crazy. But that is feed-forward neural networks in a nutshell. Very simply, it's just a complicated weighted sum, so that all you get out at the end of it is a true or false type statement. It's a fuzzy logic type of a function. But since we're at an actual programming conference, I thought I would focus more on implementation. What can you really do with a neural network? And to preface this example, one day, being the avid foreign language student that I am, I went to Google Translate and I started typing in a German word, and lo and behold, Google, in all of its infinite wisdom, said, "Would you like to translate this from German?" And of course, yes, I did. Now, thinking about this, I wanted to figure out how on earth does Google do this? It doesn't read my mind, obviously, because I don't have an API on that. And I mean, I suppose they could do some sort of a stem hash lookup. You could build an enormous distributed hash and look up stems. That's probably what Google's doing. But I wanted to figure out what's a really fast way of classifying something like gesund, which is a German stem, into German. And of course, since this is a talk about neural networks, we're going to use neural networks. But specifically, I wanted to bring this example a little bit down into very specifically about what we'll classify, and it's only these Latin languages. Now, I could have thrown in Chinese and Japanese and Hindi and many other languages, but that would kind of be cheating because when you see a Chinese character, it's Chinese. So those kinds of languages aren't as difficult. But these languages like English, German, Polish, Swedish, Finnish, they all have Latin characters, a little bit of funny umlauts and O's and whatever. So how would we do this? How are we going to do this? The first step in all machine learning problems is to collect data. Data is really the most important thing in machine learning, because without data, you wouldn't be able to learn anything at all. Machine learning is all about inductive reasoning. It's all about taking the data that we have and determining a particular pattern out of it. So data is really important. And again, I wanted to make it easy on myself, so I just used the most translated book in the world, which happens to be the Bible, because you can get it for free. There's no copyright infringement, nothing like that. I'm not doing anything special except downloading the chapters out of Matthew and Acts. But this data is freely accessible, so there's a really good corpus of data of tagged text. But as you can remember, neural networks are about zeros and ones, and text has nothing to do with zeros or ones. So what exactly are we going to do? We could do a lot of different things with text. We can split it up into stems, words, frequencies. Most likely Google is probably using stems because that's the right way to do it, and it's probably more accurate. But what if we could do it with frequency of letters, just based purely off of the amount of times that a letter shows up in a sentence? Now, looking at the data, I just extracted out the frequency of letters sorted across all these different languages. You'll see that there is somewhat of a characteristic. Now, it's not perfect. It's not like we can just fit a line to it, but there's something there. And I don't know if any of you remember this show, but there was a show called Ghost Rider, and I remember this episode really well where they cracked the code because they realized that English has a lot of E's in it. Well, this is pretty much the same thing. A lot of languages have these characteristics to them in that Polish has lots of Y's and Z's, Finnish has a lot of everything in it for some reason, a lot of vowels, they use a lot of vowels. English, of course, uses a lot of E's. But this is useful because we can actually use this. There is something there that maybe we can't intuitively do in our brains, but we could build something to learn from this particular data. So now we're at the point where we actually need to build a neural net. And a lot of people would start loading up IRB and screwing around with many different gems like T-Learn or Ruby ANN, which stands for Artificial Neural Nets. And that's perfectly fine. You can spike things. But I personally believe that test-driven development applied to machine learning is a really great approach, because when you're approaching scientific-type problems, you're writing down a hypothesis, testing against it, and then iterating over and over and over. It's very similar to the red-green refactor cycle that everybody knows. So if we were to test-driven develop neural nets, we would really need to test a few different things, and that is testing the seams, testing whether our model over or underfits the data. Now, the model conceptually will look something like this. I couldn't fit it all onto this slide because there's 54 input nodes, whereby there's 54 unique characters across all of these different languages. There's a bunch of hidden units, imagine 40 or so, and then 6 languages, which are just bits. Testing the seams, which we need to start with, is really focused on testing this part right here. So to make very quick pseudocode, which I'll actually show you in just a second, I just wanted to point out that the overall test would be making sure that what you're inputting is correct, making sure that everything adds up to 1. So, for instance, for every vector, they should add up to 1. So think of it as each node that comes in, the character nodes, should be a probability of that particular character. So if you had a sentence of A, B, A would be 50 and B would be 50%. So that's testing the seams, very simply. Now, secondly, we need to test for underfitting. And the idea for this is that a lot of the times mathematical models will either underfit or overfit data. And what's hard about neural networks is that it has this internal rate of error. So as you remember from the little slide where the guy's walking down the valley, we're trying to minimize the error. But unfortunately, what ends up happening is over iterations, let me get to it, over iterations where a neural net is iterating and trying to get better and better and better, what will end up happening is the error, the internal error, will keep lowering, but the real error will do this little polynomial type thing. Now, the reason for that is because over time, the neural net will just keep remembering things. So instead of teaching it all of the inputs and all of the outputs, which we could do, we could just load everything into memory and make this massive decision tree. What we want to do is we want to make sure that we're minimizing both of these errors. And the way you do that is through something called cross-validation. And cross-validation is a very simple idea, where you have a data set, you split it into two parts, where you have validation and training. And the training set is what you train the neural network with, and validation is just how you calculate a real error. So that's a very simple thing to do. You just split the data into two pieces, and then you calculate the real error as opposed to what the neural net is telling you the error is. And that would simply look something like this. For each language, it trains cross-validates with a 5% error rate or below. Now, the important thing to point out here is that it's not important what the error rate is. It's just important to write down your first assumption so that when you actually get all of the code working, you can tweak or you can raise up the error because you don't care anymore. And lastly, I wanted to give one little plug to something called Occam's razor, and that is this idea that if a neural network takes 50,000 iterations to complete, it's probably not a very good model. Occam's razor is all about the simplest solution being the best. Now, implicitly, we can kind of test for this, whether in test speed, but on the other hand, we can also set a max iteration in a neural net. And that's what I've done. So that's a lot of concepts and theory, so let's actually look at some real code. All right. Wow, this is... Okay, so let's look at the seam test really quick. Basically, what I'm doing here is I have all of these characters, A through Z. This is a really nasty character, which is it's a UTF-8 space, which I'll get to in a second about how nasty that is. Here's a bunch of umlauts and funny Polish characters I don't care about. And really what we're doing down here is we're asserting that these vectors that I'm making must have A through Z. I want everything to be downcased. I want them to be unique. And I want them to sum up to 1. Now, getting back to this UTF-8 space character being such an annoyance, without a seam test, without the test, I would have probably never found it because it wouldn't have notified me. But all of a sudden, when I was running this test and I was looking at the output, it was saying, oh, one of your unique keys is a space. And I'm thinking, that is total crap. Like, I don't want a space. But having the seam test totally saved me in that. Really, this is a simple class. Now, getting into the cross-validation test, what I do here is I split the data into the Matthew verses and the Acts verses. I make this little helper function which just compares the network with another text file. I compare both of them, and then I run it. Now let's actually run that. Now, I wanted to actually show you what this looks like in a production type setting, because what's really awesome about this using a neural net is how ridiculously fast it is. It's pretty much like taking this O of n thing to O of 1, but even faster than O of 1 because it's not a very big hash. It's just a weighted sum, and that's all it is. So here is my little web app, and I type in gesund, and German shows up. Fjallraven. I think that's a Swedish word. I want to say. I don't know Swedish, so I loaded these up. These are just little snippets out of. I don't speak Finnish either, but supposedly that's Finnish. Let's see, some German, Norwegian. I like how Chrome's trying to translate this for me. That was really nice of them. Polish, Swedish, and the eternal question that I wanted to throw in here is what language the Swedish chef actually speaks. English, Polish, is Bupenkern. He seems to speak a lot of English from what I've seen, and some Norwegian, Finnish. So I think the answer to that question is that he's multicultural. But there you have it. What's really interesting about this, and I'll show you actually right here, is that every time it's actually hitting this, and it takes absolutely no time to run this because it's just a weighted sum. All it is just taking zeros and ones, weighting them together, and then outputting an answer. It's extremely fast. Okay, so let's get back to this. So I wanted to put this slide up here. Go to GitHub. You can actually download all of the code for this language predictor. You can go sign up for the book that I'm writing about machine learning at that website. You can talk to me on Twitter if you don't like talking to people in real life. There's some information about that, so go ahead and get that down. In conclusion, this really is just the beginning. Neural nets is an extremely vast subject. Machine learning is a vast subject, but it's so important that we learn this stuff. A lot of us are writing Rails apps, and we're making lots of data, and we can actually end up making really cool tools just based purely off of machine learning. It's a very exciting field, and I fully encourage every one of you to learn more about it. Thank you.